Okay. Hello, everybody. Now we shall discuss with you 3 to 4 interesting examples related to the subject of contour extraction and contour analysis. The first one, as shown in the block diagram here, is comparatively not complicated, but it is very interesting. The new element here we are going to use is IMAQ extract contour function. This function extracts the contour from the object and returns the contour points. So we have an array of all the points of the contour. In this example also we use a related function which is IMAQ overlay contour. IMAQ overlay contour, which is also used to overlay the contour on the image. And finally, the last interesting also function is IMAQ compute curvature, which is also used to compute the curvature at any point of the contour. The curvature profile array is returned by this VI, and it has the same number of points as the contour points array, which are returned by the IMAQ extract contour. These are the basic 3 new functions which we will use. All of them are included within a while loop, and we need here to deal with a grayscale image, and within this function the image also is thresholded within a given range, and this range is adjustable by the user. So we have here the input as an image which we read from a file. And this image, as you see, is fed here to the IMAQ extract contour. In addition to that, we need region of interest descriptor to be fed to the IMAQ extract contour also. Now you know how to draw the region of interest by right-clicking on the image itself, and through the selection of property node, we select the region of interest. Here, the region of interest could be any shape. It could be a line, it could be a rectangle, it could be a circle. It depends what you are going to draw in the image. At the input side here also, you have to decide the direction of analysis on the image, from right to left or from left to right, up to down or down to up. And you have to consider if the region of interest is a rectangle or it is an annulus. If it is an annulus, you select the appropriate case here. If it is a rectangle, you select also the appropriate. Here, I have selected rectangular, and the analysis will be from right to left. It could be from left to right, up and down, as the situation requires. But this is under the responsibility of the user. He selects according to the situation in the work. The other input also here, you have to select between 2 or 3 options here. If you want the search to be closest to the search start, or maximum length, or strongest mean gradient change, I have selected the maximum long length. So this is the 3 input values or 4 input values you have to decide before running the program. Also here we have the curve extraction settings. If you go to the front panel here, the curve extraction settings. You have to decide the edge threshold. The default here is 75, sometimes it is 30. You can adjust it according also to the quality of the image. Also, you can select between 3 settings for the filter, fine, normal, or contour tracing. And also other options here, which normally you do not manage them that much, but you have also, I wanted to say you can select or change these values as requested, as requested by the situation in the image. Now on the output side here, the output is fed to this new function, which is going to compute the curvature. And the output directly of this element feeds the IMAQ overlay contour, which overlays the contour on the image itself. Here, the contour could have any color. You decide which color here when you overlay the contour over the image. Here, the curvature profile output, it is here an array, as you see. It is given in pixels, and it shows how they deviate, how the pixel, it is in pixels, and it shows if it is deviated that much or very little from the 0 point. The input of the compute curvature element here, this is related to the kernel width, and you also can adjust it to improve the search and the quality of the output. Here we introduced a time delay for the output to stay on the front panel. After the elapse of this time, the display finishes. If you want to see it, you can go to the front panel. It is shown there. Maybe I show you it. Well, here it is. I have put here about 10 seconds. You can manage it upon also the situation. If you consider the outputs here is the cluster, array of clusters. Indeed, this is an array of clusters. 1, 2, 3, 4. These are the points of the contour, beginning from a point and ending with the last point. They are extracted twice with different modes, so that you can compare them between each other, but they have, as you see, the same values, which means everything is normal. If you go to the block diagram here, you see the contour points could be shown from this array of clusters at the front panel, or could be extracted from IMAQ get contour information function, which also gives the points in pixels. And also you can draw the curvature profile in pixels. Here, the curvature profile of pixels, and here also you can get the same answer. So you can get the same answer in different two ways. Well, I think this is maybe the most important points we need. I wanted to show you here. And now I shall try to demonstrate with you how the function works. So the image which we have is this battery bracket, as you see. And as noted here, I am going to use a rectangle as the region of interest. When I enclose the image with a rectangle completely, as you see here, and run the program, you see the whole image, the whole contour of this piece is shown in red. Of course, to demonstrate that for you also, you can go to the block diagram here and see. Try, I cannot change it without stopping. If I change it to, let me say, another, maybe blue, not that good, yellow type, yellow color, now you shall see it will become yellow when I run the program. It is now yellow, as you see. It is a yellow surrounding all the object. But it seems to me that the red color is better, giving better contrast. So I go back and fix it. Okay, now it will be, I think, looking better than the yellow. Sorry. Okay, now let me stop the program and suppose that I want only to see this portion, this part of the image, and to examine only to find the points in this part. So logically, I am going to draw a rectangle around this part, and now I shall see, as you see, the red side here begins from here, and I see the contour around the required part, and here the points here, X and Y, for each in pixels, for each point of the contour decided by the rectangle. If I want to see this part, I go this here to this side here, I stop the program, and I go here and draw for example, the rectangle here and run the program. And as you see, we are working now in this portion here in red. Of course, we can select any part of the object and highlight the part which we are interested with, and you will get here the points which we are seeking for. Suppose that I am interested to figure out the contour of the circles from inside or the curvature at the output here from of these circles at the output. So I have to go to Anolas, and I have to stop it first, and then now I can draw and run the program. And now I shall have stop it and run it now. It must show. Why it is not showing? Well, let me try it here. Okay, now here it is okay. Yes, there is a problem here. Where is the problem? The problem is when you go to the block diagram here, it was written right rectifier right to left, but now I am working with an analysis. So I need to change this to analysis from inner to outside to outer or from outer to inner. Let me take it analysis from outer to inner, for example. Now when I go to the front panel and run the program here, as you see, I want to shift it first, and let me mark it now as requested. And when I run it, it will show, as you see, the contour in red inside here. If I want to have the contour of this small circle, of course, I can go there. I stop the program and go here and expand it. And then I shall have, as you see, it is in red. It is shown in red from inside. I can change it instead of from outside to inside to the opposite. And this is available here. Annulus outer to inner. Now I can put it annulus inner to outer. And I go to the front panel. Let me now, and I run it. It is shown here. If I go here at this for this, I clean this one. Let me work with this one, and approximately I am putting it in the middle. It is shown. It appears clearly. So I think now we understood principally that the contour of an object could be found point by point as an array at the output. And this could be done if the contour has straight lines or curvatures without any problem. We can get the contour for the whole object, or we can get the contour also for specific parts of the object. If we consider the curvature line, as you see, there is no curves here. Practically, it is straightforward at about zero. There is no deviations in pixels between any point and another point. This is the normal case indeed. This is the normal case. So as you see here, the curvature profile is shown as zero because here it is about zero. Yeah. And that's it. So now we understood that contour extract is possible, and this is very useful, of course. In future, you will see that you can get the contour of a given image and compare it with the contour of a similar image and find the difference if you want to see the difference between them. Okay. So we close this program and move to the next one. The next one will be, as I remember, it will be also related to, edge detection 15.1 or 15.2. Let me have a look at 15.1 and show you what is there. Because I have modified some of them, I am not sure that this is the case which I am interested to show you, but let us try. If I run it here, Ali, let me try it, run it. It is the same, it is working. So this function, this program, as you see also, deals with IMAQ extract contour. And I am working with an example with a grayscale at the beginning. From the beginning, it's a grayscale. Reminding you with the essentials here, it's the same here. This input, you decide how to move through the region of interest here from right to left or left to right, up and down, or down to up, and so on. So you know this. And the function here needs the image itself and needs, of course, the region of interest descriptor, which is fed from the other side. And here, curvature extraction, this is the settings which you can select as I showed you before. So it is the same as we did before, and here we will have the arrays of clusters which define each point of the contour. So the interesting here is the example itself. I have selected for you from the images which are offered by night vision. I selected this image and tried to demonstrate how the function works, how we can find the contours and define them. So let us look at this one here. I want to define the area, as you see, as much as possible to be around this big black particle. And when I run the program now, this is the region of interest now for me. Here it is square. When I run the program here, you will see that really it is shown as red, and it is selected this area and defined the contour and gave me the coordinates of each point of these contours here. Also, it gave me the curvature function. It is around 0 here. As you see, it is practically 0, from 0 to 0.6 or 0.5. It is very low value. If you put here the, for example, 1 as we have seen before, you will see that it is around 0, oscillating around 0. And really it is shown here also that it is not that fine too much, but it is completely describing the edge. If we, for example, select another object, this black object here, and run the program will define this area contour and the values related to this contour, and also it will show somehow how these pixels are deviating from one to other. And maybe it works to select the last one here and to show you also that it will be selected accordingly. As we look here, it is a smoother change of the contour, and look here, it is really also smoother and around 0 most of that time, and only it is vibrating here, oscillating here at this region. Suppose we want to work with a very small particle like this one here and surround it with the square, with the rectangle. Is it detectable? Let us run the program and see. Here, look, it is detected and it appears as a dot, and it has its coordinates, of course. And you see also the profile is somehow deviating about 25% from 0, and then it comes to 0 when it gets out of it. If you go to a moderate, let me say, shape like this, I think it will be normal with this. Look, yes, here the fluctuation is about, in percentage, 6% from 0, and it is fixed. And anyway, it is also fixed. So I think this is all about this function, and it demonstrates to us how we can easily use the IMAQ extract contour function. Yes, and here also I did not forget to show you that the output here, the points, which are an array here. This array, I can find the size of the array size. Let me fix it here. Array size. I can find the array size, and this array size gives the number of points. So the number of points here found at the last time was 73 points. If you consider this case, of course, it will be much more. If you go back here and run the program again and look at the number here of points, it is 293 points. It is a lot of points which are sensed. This is 1 point here. This is second, third, fourth. So we have about 300 points like this one, which compose the whole contour as you see here. Okay, I think it's good. We go out and continue discussing with you. Okay, now let us go to 15 to extract circular area. Also, maybe it's interesting thing for you. Yeah. Let me enlarge it a little bit. What is there? Yeah. So what do we have here? We have a path to the file where an image exists, and we read this image here. And we display the image here. This is the displayed image. Now, some work, it is interesting here, some work around this. What we are going to do? We are going to extract the circle which exists maybe inside this internal circle, or this internal circle, or this one. We want to extract it as shown here. But we extracted it differently. I have used 3 or 4 methods to do that for you. Which is functioning at the moment now is this one here. At the block diagram, at the front panel, I have created a cluster, this cluster, as you see here. And I have defined the points which describe this circle. If I put the pointer in the middle, I can see that it is X dimension is 365 and Y dimension is 205. I put it 365 and 208 with little deviation, no problem. So I have put here the X and Y coordinates of the center of the circle, and I have assumed that this circle has 2 edges, one of them with a diameter, with a radius equal to 60, and the outer one equal to 61. I have added only 1 pixel to describe the thickness of the circle. Concerning the rotation, there is no rotation here, so the angles at the beginning or at the end is the same. It is stationary. It doesn't rotate. So what I have done, I have created a cluster here. This cluster appears at the front panel here. It is this one. Now here I create a bundle by name. Sorry, I don't need it. I need to write its name. Bundle by name. And connected the cluster with the bundle by name. Automatically, the values here written are the same values which are written here. Center X, center Y, inner radius, outer radius. These values automatically appear in the bundle by name. And here I connect to each of them its value. Now I have the output here as a cluster. And this cluster now feeds the convert from annulus to region of interest. So now I have converted the annulus, which is here, and is now I consider it as a region of interest with this descriptor. And this descriptor is fed to region of interest or converter of region of interest to mask. And the output here will go to the mask. So everything on the image will disappear, and only what will stay there will be masked, and what will stay there only is the region of interest. If I run this program now with this situation, I will get the same shape. Here it is fixed, doesn't change, because I have fixed these values which represent this circle. Now I will show you how we can do the same with other configurations, with other means. So this output, this cluster now, I will open this. It doesn't exist. And instead now I will connect this object to it. What is this? This is here. This is also another way to figure out the parameters of the circle, and the output will be as a cluster, which is matchable with the annulus to region of interest converter. How this comes, it is not difficult. I showed you in an example. You go to the vision here, select machine vision controls, select IMAQ circle, and now you put it here. You will get the same as you have here. It is empty. Now I filled these values, center X and center Y, and the internal and external radiuses and angles with the same values which I used here. They are the same. This now is not needed, of course. So now this, which I created at the front panel, will appear at the block diagram as this block. And this block now I connected with the converter of annulus to region of interest. Now the system will should give the same output. So when I run the program, I get the same circle. If I put it in the center here, approximately, I'll get 367, 365. The X and the Y is 208. It's exactly as I have described, as you see. Now, if we go back and see also what we can do, I have to cancel this now again, as I did before, and show you that I can create directly an array with the given values of the region of interest, and convert this array to a cluster, and connect this cluster with the converter of region of interest, of annulus to region of interest. So here you see, here, this is the array which I created with these values exactly as they are here or here, they are here. And now this array appears at the block diagram in blue as here. This is a converter which converts the array to a cluster. And now I connect this cluster with the input here, And if I run the program, I shall get also the same answer. It doesn't move, exactly the same. Now I demonstrated for you 3 ways to do that. Okay, let us do that with the last way to do it. As you see here, we created a bundle function with these given inputs of x, y, inner radius, external radius, start angle, end angle, and connect them with this zero-valued cluster. And now the output, this now I shall open, it is not necessary at all. I shall connect this with the input here. And again, if I run the program, I suppose to get the same answer. I hope that this is interesting for you. This is really different techniques to realize the same thing, but I find it very useful to show you what are these. These are just some kind of improvement to the circle which appears as the output. This is an inverse function, IMAQ inverse, and then I use the BCG lookup function here, and the output image 2 here is the output which we see. This output, of course, could be seen by using different palettes here. Maybe it is now at the temperature, at the rainbow, it is like this. Okay. Well, I think that this is also an interesting thing for you. Let me see what I can show you also. Example number 16. Let me open it and try to discuss it with you. Okay, so here we are. Let's go to the block diagram to see the block diagram. Sorry. Here it is. Aha. This is also interesting example. Here we shall use a new function in IMAQ Edge Tool3. I'll show you it now, but 2 words about it. IMAQ Edge Tool3 finds the edges along a path, which is defined in the image. So you have an image, and you decided to draw a line maybe as a path, and you want to see how many edges will cross this line. And you want to have the number of edges there which are cutted when you cross them by this line. To find the function IMAQ Edge Tool3, as I remember, you have to go to machine vision. No. So to Caliber. IMAQ Edge Tool3. Of course, there is a lot, as usually, written about this function. Sorry. Here it is. And as you see, it has the input, which is the image of interest there, where we want to find the edges and where we are going to draw a line, for example. So the input here is the image and the descriptor of the region of interest. And here we need to show some important necessary things you want to show for the program to work, not more. And the output, now I'll show you. Of course, if you want to see them here, you have to go here and see process. What do we mean by process? Because here process determines the type of search you are going to do. Do you want to get the first, well, through this line which you have drawn, you will face the maybe a number of edges. Do you want to get the first edge, or the first edge and the last edge, or you want to get all edges, or the best edge? It depends. Of course, the best edge here means the best edge from point of view of contrast, which has a high contrast. And they have also code numbers. You can use it instead of using these titles. It makes no difference. So now you know what this function and how it comes. And now let us try to understand better about it. So here is this function. Here is the input which comes from the image. Here is our image. We have read the image here. We have shown the image here. Now we have fed the image to the IMAQ Edge Tool3. And as we know the image, we can find the property node of the image. And from here, we select the region of interest. And this region of interest now also is feeding IMAQ Edge Tool3. And these are the settings I am telling you. So you can expand it and select whatever you want. I have selected get all images, all edges which can face you. At the output side here, you will have at the output edge information. This is a cluster. From this cluster, I have extracted, I wanted to see the number of elements, the size of the array inside this. This is an array of clusters indeed. Here, these two brackets means an array, and these different small squares represent yes, they represent a cluster. So this is an array of clusters. So here I find the dimension of the array, which is the number of edges which is going to happen. Here it will be shown a number on the front panel, a number of edges. Okay, what else? So now we know this function inputs and outputs. Only one input here, which is settings, which you may need to change sometimes. Really, this is shown as a constant. Some people like it this way. Some others want to see it with some description there. You can cancel it. I can finish with it. And now it is shown as you see, a control. When I double click it, no, I show it back. So when I go sorry, when I go to the front panel now, here is the input front panel. Here it is down. where I put it. Global rectangle, not it is this one, not this one. Here. No, not this one. Let me double click it and see again. No, I will cancel it and create it newly so that to be sure. So I go here, right click and say create control. This is the control. It is called edge options. When I go here, I'll find these edge options. Where they are. Here they are. So some people, as I told you, prefer to have a look at it here. What are options you are going to work with? The kernel size, for example, here it is given 3. You can have it 5 or 7 or 9 or 15 in order to improve the quality of the image. Minimum edge strength, data processing method, you have to select whether you want it as an average or median or maybe again average or median. So, and of course, each of these things, if you don't know about it, you know about it through the help page. Let us have it in this shape. There is no problem with it. Now we go back to the block diagram here and see what we can do. So up to now, we have the IMAQ Edge Tool3 with its inputs and its outputs. And now, what do we have? The descriptor, which feeds, and the image also, which feeds the Edge Tool3. Both of them also feed IMAQ profile, or region of interest profile. This is the image, and this is the descriptor. They feed the IMAQ region of interest profile. This function, we know it, and we worked with it. And here it gives a waveform graph as the output. And here at the other outputs here, as you see, we extracted the rectangle positions here because this function here, IMAQ overlay line, here is a line, you remember. We worked with this function also previously. This line has 2 points characteristic for it, and these 2 points, each of them has 2 coordinates, the x and y. So we took x and y for the first point, and then we bundled them together to compose a cluster, and we took the other coordinates, bundled them to have another cluster. These 2 inputs now feed this function to get at the output the line which is going to be drawn on this external image. So what I am going to do, I am going to display the image externally, and there I am going to draw this line. And now this line, which is drawn on the image, will cross different edges. This function will tell me what is the number of these edges, and this drawings here will show me how these edges look like. So we go back now here. I have selected for you this image. It is a standard image of LabVIEW ALU, which is called BMP type. I have drawn the line of interest. Here is the yellow one, as you see. So it is characterized by 2 points. The upper left point here and the lower right point here. Here is their coordinates. Left top and right bottom. When I run the program, now the external image will pop up, and on this external, I will draw, or there will be drawn this yellow line. So when I run it, here I have run this line, which cuts this particle, and you see now I have an image, an edge here. Here it is white, somehow white. The pixels are high. Now it is black. The pixels are low. Then I go from black to somehow white. But of course, the image here is not really binary. It is grayscale. So here there are some ups and downs, which our glasses doesn't feel that, but the program feels it. If you run the program now, you will see this. You will see that from the high position, the high level of pixels, we go down to the low. Now we are high here, and we go down. This is one edge. And then, as you see, it goes from down to up here. In this area, as you see, it is not that white. It also goes down and up, and then it goes up. Let me, maybe better to run it newly for you, and you will see. Here the image. Why it is not running? Everything is okay, as I see. Run it. Invalid region of interest. Okay, we shall do it. Why doesn't it disappear? No. There's a rectangle. I don't want rectangle. This is normal information because I do not receive. It is there. It should be hidden there. Okay, okay. The image is somewhere hidden. It is drawn now conversely. So when I draw this rectangle, I have drawn at the same time this line. Let me change it. Suppose I'm here. When I draw, I want to go to another place here. Let me draw it here. Now when I run, as you see here is the line already existing. And now I go from high here to low, from high to low. Now it is low for a long time. It is low, and then it becomes high. Now it is again high. Now it is high, then it goes low because it crosses this object, black, and it continues to be low. It is here now, and then it comes high for this portion, and then it continues to be high a little bit with some disturbance, and then it goes low here, and then it becomes high as a spike in this area, and then it becomes low for this area, and then it becomes high again. So everything is okay. There's no problem with it. How many edges we have? Here they are 10. Let us try to count. This is one edge from high to low. The second one from low to high. The third one, the fourth one, the fifth one, the sixth one, the seventh one, the eighth, the ninth. There are 10 here. I didn't count this one here, the small one. There are 10. Of course, we can make it simpler if we only work with a small. Let us work with this one, for example, and now when I run it, as you see, look, the line here crosses the black. It was high, it became low, it was high, it became low at the beginning, and then it becomes high. It is very seen, very clear. So the number of edges, 1, 2. Number of edges, 1, 2. So I think the program deserves to be discussed with you. And here, of course, we have statistical information about the line or region of interest all over this rectangle. We have the minimum value of pixels, the maximum value of pixels, the mean value, the standard deviation, and the count, how many, the number of pixels there. And the pixels coordinates, as you see, we do have them also if they are required, but this is not the whole number here. Here there are 104 pieces. You have to extend this one completely to see all. Yes. And that's it. So I think this lecture was fruitful. We have discussed a series of interesting examples, and I hope that you have found it interesting also for you, and waiting to see you in the coming lecture, and goodbye.